Okay, so in today's class, what we will see is the continuation, and you know where we have stopped in the last class. So I am putting a box here. Okay, so one cannot be solved, equation one cannot be solved, but instead of that, the consequent differential equations that are going to appear after substitution of the Lagrangian, that only you can solve. This is the equation you got, and remember that this is your differential equation. So after substituting the Lagrangian into the Euler-Lagrange equation, that gives you a differential equation, that is this one, and then you'll have to solve this one. Okay, so therefore you cannot directly ask the question, can we directly solve the Euler-Lagrange equation itself without knowing what is the Lagrangian? So it is not possible because the equation is still in an unknown condition. So we are interested now to make a connection between these two things. Equation 2 and equation 3 does not appear the same. Okay, there is no identical appearance. So now the question is that, can you do some kind of rearrangement? Then that is your F over, then equal to mass times the acceleration is nothing but the time derivative of x dot. Now we are going to deal with one dimension. So let me therefore write down here, otherwise you will ask a question why f is not having a vector here. F should be a f vector, right? Then a should also be a vector quantity. So a doubt will come. So therefore what we will do is, we will consider the situation in one dimension. Consider the situation in one dimension. So in one dimension, what happened is, you don't have to attach the unit vector along the x-axis. That's not required. Only x-axis is there, so you don't have to ask in which direction. If at all you ask, always the answer is along the x direction. So for that reason, everything magnitude is enough. There is no need to write vector. That is what I am trying to say. So now what you understand is that acceleration is written as d by dt of x dot. Now you know what we are trying to do. What is the reason for writing like this is, first thing is we are bringing a dot notation that will be in what do you call, in conformation with the equation number 3. Okay, we would like to match equation number 3. That is why we are trying to do some kind of rearrangement. And we also write d by dt of x dot because d by dt is there in equation number 3. Okay, these are some of the plans. Because of the appearance of equation 3, we also try to do something like that. And then can you do further? That is the question. We can do still more work on this. That is equal to, we can say that m into d by dt of something we can do here. Now what you can do is, let me write down here something additionally, which is very simple thing. So if there is a x here, how we can write down? So x can be written like this. I write x square by 2 and then this is a d by dx. Is it okay? So what is d by dx of x square by 2? I will be getting x. So therefore in this method you can rearrange once again, and therefore now I have x dot. So x dot has to be replaced in this particular style. So this is the idea that we are going to use, and if we are going to do that, we will now write down that this is dou by dou x of, this candidate will become x dot square divided by 2. That's all. It's once again a small rearrangement. Now only doubt that you will get is, this is a d by dx. Okay, this is d by dx. Here I have written dou by dou x. So why did you write partial derivative? Like that one question will come. The answer will be, of course, you must be able to get the answer. Now see here, now we are considering this in the one dimension. So automatically when you are moving to the 3 dimension, this should be a partial derivative, isn't it? For one dimension, there is only one derivative, so all derivative is total. That's why it is d by dx. If you are going to have a 3 dimension like this, each direction will have its own derivative. Dou by dou x for the x direction, dou by dou y for the y direction, dou by dou z for third direction. And you already know the reason for the partial. Okay, why it is called a partial, you know. Partial means it is a contribution. The x-axis gives this much amount of contribution, y-axis gives this amount of contribution, and z-axis, what do you call, the mechanical system, gives that amount of contribution. So each 3 of these people give their share. That is called contribution. And then that total is what is called the total derivative. Okay, so ultimately we say that the total derivative is given by the sum of all its partial derivative. Partial means partial contribution. It is their share to the total. That is why it is called partial. And now it is clear that m times this can be written down like this. That's fine. Then after that, can we do any other small change? We'll do. This is not a big one. Mass being generally constant, let us take it inside. So this mass can go inside, and therefore I can write down that this is d by dt of dou by dou x of, I can now write down m into x dot square divided by 2 and then close the bracket. And that's all. So you have taken the mass inside. Now why do you want to take mass inside? Is you already know that half into m into v square is what is the kinetic energy. So this is something there, something that you know, or it stays in your mind. Now you see the appearance of half mv square has come here. You now see there is a half, there is m, and this is the velocity square. So therefore somehow we have rewritten in such a way that half mv square comes, and that's the kinetic energy is there on the left hand side. Oh sorry, right hand, this is right hand side, okay. But what is there on the left hand side? Let me simply write down that this is minus d by dx of, you have a v of x. That's all about it. This is what we have. So therefore on the left hand, this is now there on the right hand side kinetic energy, and then on the left hand side you have the potential energy. So therefore based on this you further think and rearrange why the kinetic energy should be there only on the right hand side, why it cannot be there on left hand side, you ask. Similarly, potential energy is there only on the left hand side, it is not at all there in the right hand side. So what I am trying to do is try to ask this question and bring the kinetic energy and potential energy in both the places. That means on both left hand side and right hand side I want to have both kinetic and potential energies. That is what I want, I am interested in. So if it is the case, you can write like this. So what we can do is that it is the, let us say that we are going to bring this inside. Maybe I will make one more clarity for this. Let me write down for clarity one additional step. Okay, this d by dx, once again remember this is in the one dimension, and if you are going to a higher dimension, partial derivative will come. So let that be clear, for because the same thing we have done, this should be done on this side also. Oh, here the one mistake is there. I think, yeah, is the dot is there. Did you observe this? There is a dot here because x dot square, right? So that is missing while I am writing. Okay, that's all. So on this side I can write like this. This minus I will bring it inside. Okay, so I'll write down that this is 0 minus 0 plus this is v of x. So I'll write like this. That's all. So this is the clarity is there that we can now proceed for the higher dimension. Then that would be equal to, on the right hand side, now you can write almost similar to this. Now we can write down dou by dou x dot of. Now here what you do is, there is a 0 plus of this quantity is there. So therefore, now you ask the question, what happens if the second term is also present here? That is, you yourself ask if it is present, anything is going wrong or not. So what is the second term that you have? You is minus v of x. So I'll write down the minus v of x here. If I write like this, whether anything is going wrong, you ask it. If it is going to be wrong, we can't do it. But now, interestingly, v of x is a function of x only. Here the derivative is with respect to x dot. Therefore, x dot will be absent in v of x. That means the derivative will be 0. Therefore, you can add anything you like here. Not only v of x, you can also add any constant. Nothing will happen to the original equation. So since you have that kind of freedom, that is called arbitrariness. Since you have that kind of arbitrariness, we are going to make use of that arbitrariness to add minus v of x here. Because why did you add means it is there on the left hand side. I want to make both of them similar. That is the idea. And now you ask the question, now Kinetic energy and potential energy is present on the right hand side, but on the left hand side kinetic energy is not present. So you ask the question, can we bring the kinetic energy to the left hand side? Can we add it? Bring means can we add instead of 0? 0 is already there. Instead of 0, can I add kinetic energy term which is m into x dot square by 2? Can I cut the 0 and put this fellow here? That is the question. 0 is not equal to this, but can you add m into x dot square by 2 in place of 0? So you have to think and tell. The answer is yes, you can do, because the derivative is here x. This quantity is x dot square. So there are no dependence on the x here. Therefore, this first term differentiation, if you perform the differentiation, this fellow will go to 0. Therefore, it doesn't matter whether 0 is there here. So whether 0 is there here or whether m into x dot square by 2 is there, it doesn't matter, because dou by dou x will make it 0 ultimately. And therefore, we are left out with minus b of x. And that's all about it. And that is equal to, simply copy this. Okay. The right hand side I am not once again writing, simply copy. So ultimately what happened is, finally we have got an expression like this. So if you can see this particular object, which I am going to put it in this pink color for example, this entire thing is nothing but your kinetic energy minus potential energy. And the same thing is there here also. This particular object, it is the same kinetic energy minus the potential energy. So therefore, what we will do is, so let us call the kinetic energy minus potential energy as something, whatever symbol you give, that you call it by that symbol. And finally, we say that dou L. So let us say that this is this L, that we'll call by whatever symbol you like. Now we will be having like this dou by dou x of this fellow. This is the L here, which is equal to d by dt of dou by dou x dot of this one, dou by dou x dot of this entire thing, which is L. So ultimately what happens is, this is the Euler-Lagrange equation. So what we have done is, we have not done any derivation here. So this is very important. Okay. So this particular thing is important, that this is not the derivation. Of Euler-Lagrange equation. Okay, somehow we manipulate. This is basically manipulation of the Newton's law, and then rearranging terms and then bringing it in the form of the Euler-Lagrange equation. Now how you are able to do is, this is called the reverse calculation. Okay, you already know the answer. Answer is, you already know the appearance of the equation. That means you have to keep the answer as Euler-Lagrange equation and then try to manipulate the whatever you want. If you are able to successfully manipulate, yes, you are able to do, but otherwise no. For the case of mechanical system, you are able to do like this. But remember, as one of you asked in the last class, okay, one of your classmates asked that whether we can maintain the same T minus V. This is your T minus V. Can we maintain the same T minus V for all the dynamical system? That was the question asked. I already said that it is not possible. Okay. So for those mechanical systems, okay, that obey Newton's law, this is valid. This is very important. Whenever you consider a mechanical system for which you already know that the Newton's second law is valid, for such systems, the Lagrangian equal to T minus V that we are going to consider, this will work. Okay, but suppose if you are going to consider some dynamical system for which Newton's second law is not applicable, then for such systems you cannot use T minus V as the Lagrangian. So that is the point. That is the same point that I already explained in the last class. So now you will be able to further make the things clear. Okay, so this is the place where you understand why minus comes into picture. You understand why minus comes into picture? It is there here. So minus of the V of x is there. This is the reason why the Lagrangian is kinetic energy minus the potential energy. So that is the question that we have. So we always ask the question that why don't you consider the total energy why this will not work. Now you yourself know the answer, because when you are rearranging, the minus came into picture automatically. If you want to make it plus, which means that you won't get it, it is not corresponding to the Newton's second law. That's all. Therefore t plus v will not work, or it is not a suitable Lagrangian. So this is something which will make things much more clearer before we can start solving the problem. Okay, so this is the idea. I think we will start doing because it's already half an hour is over. I said that we will start with the simple pendulum problem, but instead of that, let us start with the small cylinder rolling on a larger cylinder. That problem is anyway slightly difficult when compared to simple pendulum problem. It would be better, let us start with this, and then the other things will be easy. Now, to make the things clear, the statement of the problem, I have drawn this diagram. Okay, now we are coming to the solution of this problem. Statement of the problem is clear to you. So let me again explain. The blue color is a cylinder. We are going to see the front view cross section of the cylinder, where the axis of the cylinder is perpendicular to our plane. Okay, it is perpendicular to the plane of this board. That is, this is the axis, this dot that is there. So because the larger cylinder is there, you have the condition that the radius A will be very, very large when compared to the B. So it's a larger cylinder. The second thing is that this particular larger cylinder is fixed. That means it will not move. Okay, it is fixed. And then you are going to assume that the smaller cylinder of radius B, this is a smaller cylinder, is kept on top of a larger cylinder, and it is going to roll down. So this is going to be a pure rolling, because slipping is to be avoided, otherwise you cannot perform the calculation. So only rolling takes place and the slipping is not there. That is the point. And now that it is going to roll down and then come. Now why I have drawn two of the cylinders here is that this is the first one, the continuous line that you have in the pink color is the actual cylinder that is there. The dotted cylinder is the cylinder that it is going to come. Okay, once it starts rolling, you imagine what will happen. If the cylinder makes 2 pi rotation, 2 pi rotation means one complete rotation, or one complete what you call 2 pi r, or let us say that, let me tell this one, 2 pi into b. 2 pi into b means what? From here to here completely. So it is going to roll down like that. When it is rolling down, this pink color cylinder, now it will occupy this particular position. That is what I am trying to say, and therefore I have drawn in the dotted line. So that's all about the diagram. And then the diagram, we have to make it neat. Only then you will be able to identify what is the equation of the constraint and other things. Otherwise things will be very difficult. You can't imagine actually what is to be written. So that's why I am taking some additional time to draw a very neat diagram. This is very important. Otherwise, writing down the equation of constraint is going to be the difficult part. So now what are the possible variables that we are going to identify is that we have to first of all choose the zero of the potential energy. So probably for that reason, let me therefore draw the x-axis possibly here. Okay, so that can be an x-axis. So I'll draw like this, and then say that this will be the x-axis, and similarly the y-axis, let us make it like this. So let me not make it dark, let it be light, so that it is only for the reference. So this is the x-axis, I will write down. There's an x-axis, and this is also the zero of the potential energy. That is the first point that is required, and this will be the y-axis, let us say. So x and y-axis is clear, your origin is clear. So therefore, what is the advantage is here, that here I will write down that this is one rotation of the small cylinder. So now what are the variables that are required? That is one important point, that is so that you can write some equation. So for that, first let us start how do we deal with. First of all, we will ask what is the kinetic energy, because that will be easier to write. What is moving? That is the one which is going to provide the kinetic energy. The larger sphere in blue color, that will not at all move. It is fixed one. So the smaller cylinder only will move. Move means, remember, in this problem only rolling. Okay, pure translation is not there. So that is why the word pure is there. Okay, if you are going to assume that it is also going to slide down as well as roll down, then it is a mixed kind of movement. Okay, pure means only one type is there. So this is a requirement, otherwise the problem becomes more difficult. So therefore kinetic energy will be given by the standard expression, namely the one due to the pure translation. Pure translation means the object itself is moving. The cylinder was here, it came here. After some time it will come here. After some time it will come here, and then it will be detached from the larger cylinder and fall down. Now that means the entire cylinder is moving. That is the half mv square. That is called the translational kinetic energy. Plus, since the cylinder is rolling, you have to add the rotational kinetic energy, half I omega square. So this is how you write down the general expression. Then afterwards, you can now simplify what is to be done. Now where small m to be assumed to be the mass of the small cylinder. We are not interested in knowing the mass of the larger cylinder, because it will not come into picture. It is a fixed one, so it is not going to move. We don't want it. That's all. Now you ask the question how to write this particular expression is. In general, you ask the question, is it a 3D problem, 2D or 1D problem? Only when that is clear, you can simplify and write down v square, because v square how to write. We have seen something like 2 classes back. We have seen how to write 1D, 2D, 3D. In 3D also cylindrical and spherical. Now you will have to clearly identify whether it is a 3D problem or 2D problem or 1D problem. So that is where the point to be noted. Now for that purpose, you see a dotted line here. So I have written a dot. This is you follow the white color cursor. Now this is the dotted line that I have drawn. What is this line is that as the cylinder is going to roll down like this, the center of the cylinder will follow this particular path. And you know what is meant by center of the cylinder? You can imagine that is the center of mass, because you are going to see the front view only, and therefore you can imagine that is the center of mass. By that, what do you mean? The center of mass is, the concept of the center of mass tells you that let it be any big object. You forget about it. Remove the entire object and put a dot there. That is the concept of the center of mass. If an aeroplane is flying in the sky and you want to do some calculation, you can do the rigid body dynamics calculation if you are going to consider the shape of the aeroplane. If the shape of the aeroplane is not important for you, then you find out where is the center of mass of the aeroplane and put a dot there and remove the entire structure. Aeroplane structure itself you remove. You put a dot and say that the mass of the aeroplane is m and it is occupying a position x, y, z, which means only one point. So you are going to reduce it to a point mechanics. That is mechanics of a particle. You are going to consider aeroplane as a particle. So that is what I mean to say. The word center of mass gives you the information that the entire cylinder can be considered as a point there. You can remove the structure. Structure means cylindrical structure, and remove only one point. That point is moving along this dotted line. Because these things you know already how it is going to move. That is where diagram is going to help. Then you tell whether this is a 2-dimensional motion, 1D or 3D motion. It is going to make a circular path. Okay, it is going to come like this, means it's a circular path. Therefore, it is supposed to be 2-dimensional motion. Circular path means we will see whether it can be reduced further because of the constraint. That is a secondary level. First thing is that it is going to be a 2D. 2D means plane. The center of mass is going to travel within a plane. That is very important. That is what I was asking the question. So plus, therefore, y dot square. Z dot square will not enter into picture. That is the important point you need to know. Otherwise, you will make the mistake in the very first step. Okay. So plus The remaining thing is okay, half into, we can always substitute what is the moment of inertia, that is okay. And then this particular thing omega has to be written down in the dotted notation. So let us use some kind of angle should come. So we will say that some phi dot square. So which means that you will have to tell how to measure phi. When I say phi dot square, phi should be there in the diagram. Otherwise there is no meaning. So therefore I will now show what is this phi here. Suppose if you draw a line from here to here. Let me draw a line from here to here. Something like this. You can draw anywhere. It doesn't matter whether you draw this one, that one. Somewhere you draw and then say that from here to here is phi. This will be phi. Because whatever you write in the equation should be there in the diagram. If it is not there, then completely it is meaningless and it is waste to write. So phi will be that diagram, which means that when it is moving, whenever it is moving like this, you will have to always measure with respect to this particular axis. You see from where you are measuring, therefore arrow is important. I will put the arrow here. So there is a line here that connects to the center of the larger circle. That is the reference point. From that point, I measure an instantaneous point. Instantaneous point. What do you mean by that is, let us assume that you put a sticker here. On a cylinder, you put one sticker on a particular point and then keep that as a, from there to there, always you measure when it is moving. So whenever it is rotating like this, you measure from this particular line to the place where you have put a sticker. So since these two things are fixed here, you can always measure phi. Then you calculate how fast it is moving, and that is your phi dot. So you'll have to understand like that. Okay, that is fine. The next level, do you want to keep a Cartesian coordinate system? You have written x dot square, y dot square. But you already know that the center of mass is going to follow a circular path. Since it is going to follow a circular path, better to use 2D polar system rather than Cartesian. So that is the information we get, and therefore you write down the corresponding expression that we have already got in some of the previous classes. X dot square plus y dot square in the 2D plane polar is r dot square plus r square theta dot square. This we have actually derived it, so you can verify that. Plus half into I into, you get a phi dot square. Like this you can write the expression. And now to simplify this, we need some more information. This is a general information we have written. Now you ask the question, okay, suddenly I have written something r here. What is this r? That should be clear. And you know that r should be the, what you call the radius of the circle in the 2D plane polar. And ask the question, what is the radius? Now the pink color dotted, this is the pink color dotted line along which the center of mass is going to travel. And therefore what should be the radius? The radius should be from the origin. This is the origin, from here all the way up to the blue color plus all the way up to the pink color. So that is the total radius that you have. And how do you know what is the value? Here it is there. A is the radius of the larger cylinder, B is the radius of the smaller cylinder, and therefore R must be equal to A plus B. So that is what you get, and that R should be used in this particular equation. And this particular equation, since you have written that, once you see this diagram and you have written, this clearly indicates that this is the equation of constraint. Therefore, and I will write down where R equal to A plus B is the equation of constraint. Now, why do you want to use the word equation of constraint? Is that is the one which is the restricted one, or you want the smaller cylinder to roll on a larger cylinder. That is how you want it to roll. You are not allowing the smaller cylinder to fly away somewhere. Okay, so because you are going to keep the dynamical system to be like that, we say that is the restriction. So you'll have to identify that this is the equation of the constraint. So that is why I am writing this is the equation of the constraint. And therefore what happens is you can now simplify this equation. How you can simplify is you'll have to first of all calculate r dot. R dot is time derivative, and you know that r equal to A plus B, radius remains constant. So when it is coming like this, it has to be here only, here also same radius, here also same radius. And if it comes down here, here also it is same radius. Afterwards, what will happen is, the once it is getting detached here, the larger, the smaller cylinder may come here. It will come out of contact, come outside, and when it is going outside, we are making an assumption that we are not going to solve it. Okay, we are trying to get the equation of motion as long as it is in contact with the larger cylinder. That is our aim. So once it leaves the contact, now you see what is the distance. Now this distance will be equal to, this is the distance that you have to calculate. Now it is greater than a plus b. That is the point. It's greater than a plus b. Such situations we are not going to solve. So under this constraint, how? So if it is the case, therefore you can now solve or we can simplify the kinetic energy term as half into m into r dot square is 0 plus r square is a plus b. A plus b is the total radius that you get, plus whole square into, anyway this theta dot square will be there. Then there is a plus. Let us substitute the moment of inertia of the cylinder, half into m into moment of inertia of the cylinder is ma square by 2 is a standard expression, where a is the radius of the smaller, sorry I think not a, right? What is this? We have to substitute the radius of the smaller cylinder. So you have to be careful whether to put a there or b there. I'll put b here because it is a smaller cylinder. So it has to be mb square divided by 2. Okay. Then there is a phi dot square. Okay, that's all. This is the kinetic energy. So fairly you have simplified somewhat, little bit you simplified, but you ask the question, is it okay? Is this simplification enough, or you have to do something more? Now there is a theta here. Theta is there. There should be theta, then only theta dot will be there. So you ask the question, where is theta? In the diagram, theta is not there. So that is why you have to be careful. Every time you see the diagram and verify whether the theta is there. Since it is not there, now you tell, now since we are dealing with the so-called standard coordinate system, you can always consider that I am measuring the angle from the vertical axis and I say that that is theta. So therefore, this is at a particular time. After some time, what will happen? After some time, the cylinder itself is going to come here, and therefore that will be my new theta here. So this is how the theta will keep changing. Okay, when the smaller cylinder rolls down. So now you understand that since theta is changing, theta dot is meaningful. How fast theta changes. So that is fine. Now there is one critical point that has to be finalized. Only then you can solve the problem. The critical point is that you are asking the question. I don't have space to write. Maybe I will write here. You try to see. Now there is a critical question. The question is whether the variables theta and phi independent. This is important question. If you say yes, answer will go in one direction. If you say no, it will be completely different. So independent means theta should take whatever value it is possible. That means in between 0 to 2 pi. 0 to 2 pi is fine. Theta also 0 to 2 pi, phi also 0 to 2 pi. The question is whether theta and phi can take its own values or one angle will depend on the other. That is the question. So now that answer is to be obtained only by looking at the diagram, and then you'll have to imagine the situation of rolling. So if it is rolling down like this, whether theta and phi will take its own value. Its own value means theta will be 10 degree, phi will be 27 degree, theta will be 3 degree, phi will be something like 93 degree. Can it take any number like that? Or theta and phi should follow some rule? That is the question. Okay, now you can easily understand. Now I will tell you what is the explanation. If this particular pink color cylinder rolls by an amount of 2 pi radians, that's what I have written, 2 pi radians, then how much distance it will travel? 2 pi into b distance it will travel. So therefore 2 pi into b is there. So that is the 2 pi is this entire length for perimeter multiplied by this particular radius. then it will come here, right? When it comes here, theta has to be here only. Did you understand? Theta has to be here only. Theta cannot come up to this. Now I'm asking the question, will the theta come here? So my question is, when the pink color cylinder is here, can this be the theta? I'm putting a question mark. Can this be the theta? No, this cannot be the theta. Only this can be theta. That is clear. Which means what? Which means that the phi angle will determine where the theta will be. One fellow will fix the other fellow. That is the meaning. The value of the phi will determine the value of the theta. Two of the angles cannot be independent of each other. So that is the conclusion that we can understand once again from the diagram, and therefore now we write the answer here. The answer is no. So they are not at all independent, they depend on each other. So therefore, then if it is depending on each other, then immediately next question comes. What is the dependence equation? By what equation these two fellows are related? Give me the relation between theta and phi. Okay, that is the question. Then you can immediately ask the question, then what's the relation between theta and phi? That is the question. Once again, it is not at all difficult. You can once again see the diagram and then say that when it is making 2 pi is the phi. You remember what is 2 pi? This is the phi angle. Remember, phi angle is for the pink color. Okay, so 2 pi, if it is making a rotation for the smaller cylinder B, smaller cylinder means B, B is the radius, then that must be equal to, for the larger cylinder, what is the angle? Theta is the angle, and for the larger cylinder, what is the radius? A should be the value. So therefore, 2 pi is an example that we have taken for understanding purpose. That is visible, right? 2 pi means something visible for you, so you can see. So instead of 2 pi, the smaller cylinder can roll by an angle phi, then the larger cylinder will make an angle theta. So this is our conclusion. So this will be the another relation holding between the two variables. So therefore we say that this is the equation of constraint. So this is the one that will eliminate one angle. Any one angle, that's okay. It doesn't matter whether you eliminate theta or phi. Any one will be eliminated and only one fellow will remain. That is the meaning. So where are the two fellows are there? Let me tell here. You see this? In this equation, this is a kinetic energy equation. Theta dot is there. Phi dot is there. You have two angles. Now, because of this equation, what will happen? One angle can be eliminated. One will go out. And therefore, ultimately, we will be left out with only one angle. So that is the conclusion, and therefore we will substitute this and simplify this kinetic energy now. So therefore kinetic energy is equal to half m into, let us simplify this, a plus b whole square theta dot square, that's fine, plus 1 by 2 mb square divided by 2 into, this is the place phi dot. Now this is phi dot, right? Phi dot you calculate. If I differentiate this, what will you get? You get a theta dot A. A is constant, so take it out. So let me take A outside. Then theta dot, then divided by B. So that much whole square. Okay. So that is what we are going to use this. So this particular equation, when you use it, the kinetic energy term becomes simplified now. And why it is simplified means, in both the places now theta dot is a theta dot, one phi dot has disappeared. That is why I say that it is simplified. And therefore you can now, let us try to do some, now hereafter there is no big work. It's basically it's some kind of rearrangement, taking derivative, that's all. Now it is quite simple after this. So m into, let us expand this, I get an a square plus 2ab and plus b square, then multiplied by theta dot square. Then this one, let us simplify this. So this one I have to close bracket, right? Yeah. Plus, let me write down like this, half mb square by 2 a square by b square theta dot square. Okay, so that is equal to, because half m I am trying to take common. So I'll take a common for both, all these terms. Then I get an a square plus 2ab plus b square. Theta dot square, I think one of the terms are cancelling. So you now understand why we are doing this. Something like this you can cancel. Okay. And half m is constant. So that will be taken out. Half m I am taking out. Then what is remaining? So what is remaining is a square theta dot square. So I can write down a square by 2. That's all. A square by 2. Then theta dot square is outside. So this equation has simplified to a considerable extent. That's all. There is nothing more to do. So we have the kinetic energy, which we are going to put the symbol T here, which is equal to this expression. I think this we have to simplify. So how much is this? This is 3 by 2, right? So 3a square by 2, because the last term we have to add. Then plus b square plus, then we have at this 2ab, that's all, multiplied by theta dot square. So that's all. This is the equation for the kinetic energy. Okay, so the expression is now hereafter, as I said, it's only a matter of simplification. Now once you identify the kinetic energy, potential energy term will be very easy. So you are going to use the standard rule mgh, that's all about it. The only thing is you'll have to determine what is the height, that is first thing. Second thing is you have to clearly tell whether it is a positive value or negative value. That should be very important. Okay, so to write down what is the height, you'll have to see the diagram, otherwise you can't write. So let me go to the diagram and now what is the potential energy means at any instant of the time you ask the question, at what height the pink color cylinder is located. At what height it is located means you can easily tell that this is the height. You draw a vertical line here. You can draw a vertical line like this. That is the value, right? You can always draw like this and tell that that is the vertical height at any given instant of time, because this line why we are choosing is this is the zero of the potential energy. So this is the center of mass. When it was here, then that will be the height. When it is coming here, this will be the height. So the height will be keep on changing depending on this particular value. So therefore you need to know what is this particular height, and that can be calculated because this is theta. And so theta is this, so this fellow is a plus b. A plus b is the total length or the radius. Therefore we can say that a plus b into which component you have to take. Cos theta component you can take to get the height. So therefore I think that is clear to you, because even there is no space to write. If you want, I'll write down here. So this must be equal to, this height from here to up to this. Okay, so that kind of distance would be equal to a plus b into cos theta. So let us copy this number a plus b cos theta into our potential energy. We'll go down. Here it is. So let us substitute that a plus b into cos theta, and that's all. So there is nothing is there here to simplify. This is b. So therefore once you have the t and v, the next things is very simple. It's only a matter of another derivative, that's all. So let us therefore calculate. So therefore let us evaluate the Euler-Lagrange equation. So which means that we will calculate dou x by dou theta dot. Dou theta dot equal to this fellow you differentiate. I will be getting mass times 3a square by 2 plus b square plus 2ab, and that's all. So the differentiation is also simple, and one derivative is over. The second derivative is dou L divided by dou theta we'll have to calculate. So that is equal to, this is a cos theta term, and you have to be careful in evaluating. Now I want to know whether it is a minus value or plus value. Okay, so you have to be careful. By that what I mean is L equal to T minus V. So why I am asking this question is Lagrangian has a T minus V. So there is a minus. Now cos theta, when I differentiate, I will get a minus sin theta. So therefore this will be a plus. Okay, so therefore I will write down that this is mg into a plus b into a sin theta. So that I'm talking about positive value here. Okay, otherwise there will be a mistake in your calculation. So this minus you have to note down, and using this minus you can simplify. And once that is what is this Sridhar outside? Hey, now only one student is coming. Sridhar want to join. Okay, admit. But now class is getting over, right? Okay, let us finalize, and that will be the conclusion. So therefore our conclusion is, so the equation of motion is that we can now calculate what happened to this theta dot. So there is we are differentiating this, right? Theta dot square. So theta dot square, if I differentiate, I will get it theta dot. So that should be there here. That's all. So now let us write down, so the equation of motion is theta double dot is equal to this quantity, that is mg into a plus b into a sin theta, then divided by this entire thing. That means m into 3a square by 2 plus b square plus 2ab. And I think that's it. And there is nothing to simplify now. Okay, looks fine, and I think you can only simplify the m. M can be cancelled, that's fine. Only m can be cancelled. Yeah, so this is the final answer. So hopefully you will be able to follow this explanation. I have been explaining with a reasonably slowly. That means you'll have to get the concept rather than going to the next problem. Okay, so our aim is not to jump to the next problem, no, rather than spending some time and understanding what is this. So this is our conclusion. So in today's class, what we have done, you refresh your memory, that we have seen why the Lagrangian should be t minus v rather than t plus v. So that is one of the discussions that we made. In addition, we have also seen an intuitive way of rewriting the Newton's second law in a form which is identical to the Euler-Lagrange equation. Okay, so this is something which is interesting. This is what we have done. So which means that this is not a derivation. Please remember, this is not a derivation, but this is only an interesting way of rewriting. This is the entire step is only a matter of rewriting the Newton's second law, which gives you a clear idea that t minus v will be a possible Lagrangian, physically, not mathematically. Okay, mathematician, if you are a mathematician, we will ask that, okay, no, don't use any other equation. Straight away try to construct some function that is suitable for Lagrangian. So like that the question will come. But we are interested in comparing this with a natural system, which means naturally occurring mechanical system. And we already know that Newton's law is right. That is the reason why people started with the Newton's law and then understand by using T minus V. That's the primary reason. Okay. Other than that, any other Lagrangian can also do the same work, but we do not know what is that Lagrangian. So that is an interesting point. And if you are going to move away from mechanical systems, a general dynamical system need not have T minus V as Lagrangian. It can be completely something different, not even with the dimensions of energy. Okay, so this is the general information, and today we have solved this particular problem. I think after solving this problem, the simple pendulum situation should be quite easy for you. So you can try to do the simple pendulum problem by yourself. And if it is the case, in the next class we will try to discuss some different topic or further continuation with this, such as symmetry. Okay, something called a cyclic coordinate and etc. So similar topics like that we can do it in the next class. Is it okay?